first speaker of today is Marc Burger, and he will talk about the real spectrum compactification of character varieties.
Yes, thank you very much for the invitation. So this is a follow-up conference on the 2017 program, which is quite appropriate because that's essentially where, with my co-authors, we started to think in those terms. So the aim of my talk is to explain the concepts occurring in the title and to tell you why we care. So the first protagonist here is going to be a subgroup of GLNR, which is real algebraic, semi-simple. So these are just the groups you know from linear algebra over the reals. Think about SLNR, SOPQ, SP2NR, and products thereof, and then you have already enough concrete examples. I don't want you to focus on semi-simple, it will not come into the open because there are going to be no proofs. I want you to focus on real algebraic, which means that this is a matrix group that is defined by a bunch of polynomials. And to keep in mind for later use that if you have a field extension f of R, it will allow you to define a new group, namely, look at all the polynomial equations defining a G, and look at the solutions now that have their matrix entries in F, and this will lead to GF. So, the second protagonist here is a finitely generated group, so F is a finite generating set. And then we have already the interesting fact that all homomorphisms from gamma into G so that's the evaluation map. Homomorphism is clearly completely determined by what it does in a finite generating set, but there is more. We can characterize the image. Well, just take any presentation of gamma and look at all the f tuples in G to the f that satisfy all these relations. These are polynomial relations. So this means that omega G is identified real algebraic subset of G to the f. And there is this slightly mind-boggling fact that, which comes from the Noether property, that even if gamma is infinitely presented, on this side, only finitely many relations will suffice. You just sort of think more about it. Yeah, maybe let's not think more about it. No, but you see, it asks the question, so you have finitely many relations imply all the others, so that means there are all these relations in linear algebra that are implicit there. How can you express this in mathematical terms? Anyway, so now we have this real algebraic set, and we're interested at homomorphisms up to conjugation. So now take the G quotient, which presents us with certain complications because the G action by conjugation on F tuples, some orbits are closed, other orbits are not closed. Here's a nice fact. is that the G orbit of the representation rho is closed if and only if rho seen as a linear representation into SLNR, remember, G is in SLNR, is some of a reducible. So these we will call reductive representations. Now the character variety is the topological quotient of the set of reductive homomorphisms from G gamma into G modulo G conjugation. And that's a topological space whose points are closed for the moment, and that's not much more. Now, identifying this here is clearly a problem in invariant theory, and the work of Richardson Slodowy tells us that the character variety is homeomorphic in a explicit but rather complicated way to a closed semi-algebraic subset of some Rn. So if G were a complex group, invariant theory would tell us that this quotient is an affine variety over the complex, Hilbert, etc. Over the reals, you can't expect much more. Well, look at group Z mod 2Z acting on the real line by x go to the minus x. So by taking the invariant polynomial x goes to x squared, the quotient is naturally homeomorphic to this half line. That's really the thing, the price you pay by working with the reals. So now comes the first central definition of this talk. So what is a semi-algebraic subset? So a semi-algebraic subset N is a finite union of sets of the form you have finitely many polynomial inequalities and finitely many polynomial equalities. So P1, PR, and Q1, QL are polynomials in n variables. So, in fact, this is sort of, when you think about the objects surrounding us, nothing looks algebraic, but everything looks semi-algebraic.
Closed semi-algebraic?
No, that, where?
The theorem is that it's closed. You work out why closed comes up, because that feels a little more surprising. From the point of view you just said, right, that everything is semi-algebraic. But closed is rare.
that's a feature that, well, I mean, I would have to tell you exactly what are the invariant functions here, and then state the theorem that a certain map is proper. Yes. In this, you're right to point this out. Closed is in general the difficult part. Exactly. It's in general the difficult part. Now, of course, these sets, algebraic subset S. As I said, these are extremely nice sets, and here is a remark that I think that is due to Whitney. Okay, completely misspell Whitney. I mean, I don't know how many H's, how many I's, how many Y's. There is at least one I, right? Here.
Second H is an N.
Okay, so he proved that S has finitely many connected components. And each semi-algebraic again. So we stay in the same category, so to speak. So that is enough information to tell you now why we care. Well, first example, the kind of surfaces we like. Then we know that the hyperbolic structures on sigma modulo diffeomorphisms isotopic to the identity via the holonomy representation identifies with a subset of the PSL2 R character variety of the fundamental group with image. So I'm going to call G the image, and then maybe everybody should have a G here. A connected component. Also called Teichmüller space. It should be called Fricke-Klein space, but now there's no, I mean, this ship has sailed. Teichmüller theory, there's nothing Teichmüller about it. It's really Fricke-Klein. Is a connected component that gives on a space that's, you know, apparently enormous a structure of semi-algebraic set. The second, and that's a great theorem of Benoit. Let's say you have a closed M manifold, and gamma is word hyperbolic. And you want to classify the projective structures on this N manifold that are the geometric structures that are locally modeled on the n-dimensional projective space. So, yeah, there's a way to, okay. And so then, what Yves Benoit proves is that the convex real projective structures on Mn modulo, again, differ isotopic to the identity. So this via the holonomy representation, well, it goes into the character, the PSL n+1 character variety of the fundamental group. You need the n+1 if you want to have a projective space to give dimension n. And this identifies it with image a union of connected components of the character variety. That means that first there is a stability. If you deform a convex real projective structure, then it stays convex real projective, and then the difficult part is to show that it's a closed condition. So this is a great theorem of Yves Benoit. It definitely tells us, well, that from that point of view, why do we care about character varieties? Because their connected components are moduli spaces of interesting geometric structures. That's the takeaway of this. Now, this business is a two-way street because you can do the following construction. Let's come back to surfaces, and then now I'm going to realize, well, I'm going to, hyperbolize my surface, which I made, and compose it with the irreducible n-dimensional representation of PSL2R. And now the object of study is what is called the Hitchin component. You can compose this irreducible representation with this injection, and you can take the connected component of this guy in the PSL and R character variety. So, hyperbolization, a very standard representation, there seems to be nothing new under the sun, right? We might as well have forgotten about that guy. But now we're going to take all representations from gamma into PSL and R that can be deformed into this guy here. So this is called the Hitchin component, because Hitchin proved that it's a R to the something. And it's a theorem of François Laborie that this component consists entirely of faithful representations with discrete image. And so now you have the inverse problem, which is, what is the geometric significance? For n equal 2, we recover Teichmüller space. For n equal 3, you recover the convex projective structures on sigma. That's all the, because you can, the projective plane has dimension 2, and you can look at all geometries on the surface that are modeled on the projective plane. Okay, so this gives enough reason to care. Now,
what is the presentation there from PSL2 to PSLN?
So this is the irreducible n-dimensional representation.
The unique one.
The unique one. You let SL2R act by change of variable on the space of homogeneous polynomials of degree n-1, and then you go via minus identity. I mean, of course, I'm telling you these things. There is no. I mean, if you look at this, there's absolutely no reason to believe all what I'm telling you. I mean, these are theorems. But I think it's already interesting to focus on the SL3 case. What's the difference between this and this? So now we're going to compactify character varieties. And so I can define what is compactification. So if you have a, let's say, if chi is a locally compact space, in our case it will always be semi-algebraic sets. Then the compactification is a diagram where K is compact and I is a homeo onto an open dense subset. And as we'll see, this still allows many pathologies. So the idea is if you know how to compactify a character variety, then in particular you can give a meaning to, as you move to infinity in the space of hyperbolic structures, can you detect the degenerations? That's an old theme, of course. But that applies to this situation, that applies to that situation. So that's the idea. So the classical compactifications are all based on the same idea of Thurston. And then it evolved either into Morgan-Schelen or a whole compactification in a more general context, which is you replace your hyperbolic structure, for example, by a length function. And now, so let me recall you how this is done in this case here, because I want to say something later about this. So I mean, for this audience, I guess you all know how to associate to a hyperbolization So you have hyperbolization, you look at the marked length of all the closed loops, and you get a map, which is a priori a map from pi 1 into positive reals, which you quotient by, which you look at up to homotety. Okay? I think everybody is familiar with this here. And then now you have replaced your hyperbolic structure with a different object. And so that different object has actually the virtue that now it is elementary to see that if you take the image and its closure, you get something compact that is solely based on the fact that the fundamental group of the surface is finitely generated. So that fact allows you to, leads to all these generalizations here. So this is the well-known, so let's call it TG bar, the closure of the image. So this is the famous first compactification. And then you're left with the, so this gadget is compact. And now you're left with the interpretation of the length functions occurring in the boundary. What are they? And that's, of course, a drawback of this kind of compactification. Now you have to think up really something, and, well, then you have the interpretation in terms of actions on R-trees, and then you have the one in terms of measured eliminations, etc. And the point is that in our approach, which produces a different compactification, all these objects you see there will be associated canonically to the boundary points. And so that's what I want to illustrate later on. So if you want to chew on something, here's a little fact, so you can ask yourself, what distinguishes a length function of a hyperbolic structure from a limiting length function? So here is what distinguishes it. If you have a hyperbolic structure and you look at the length of all the closed geodesics, and you look at the Q-linear span in the reals of that thing, so this is infinite dimensional. If you look at the boundary length function in the first boundary, then the dimension over Q of the linear span is more equal to 6G minus 6. So there is something happening there. And yeah, okay. This admits a vast generalization. Talking about these length functions, the point I wanted to make is the following pathology, which has been shown by Maxime Wolf. If instead of compactifying Gleichmüller space, you compactify the whole character variety by length functions. I mean, if you have any representation in PSL2R, then any element in PSL2R has a translation length. It might be 0, it might be positive, but you know, it's a number. Okay. So then, the following pathology arises. If you take the closure of the image of the whole character varieties, then this gadget has fewer connected components than the initial character variety. In fact, he shows there is a component in here, not Teichmüller, such that if you look at this boundary, length function boundary, this boundary eats up completely the first boundary as a nowhere dense subset. So compactification by length functions of characterized produces junk. I mean, interesting from other points of view, but I mean, if you can't even, you have a compactification doesn't even distinguish between connected components, then it's not of much use. So,
Mark, I'm sorry, but I think I missed something. Why this is compact at all? The closure of
that's essentially.
Put it in projective space.
what?
Put it in projective space.
It's an infinite dimension.
Yeah, it's infinite dimensional. So you have to show something.
What?
You have to show something. You can show that essentially first finitely many length functions will determine the rest, and then by rescaling, because it's finitely generated, you can put it. It's sort of Tikhonov's theorem. It is elementary, but it requires an argument.
Yeah, I understand.
But this argument is extremely general. So, okay. Okay, so now essentially, let's come back to the general situation where my characterized is sitting as a closed real algebraic subset. So, so what we're going to do is compactify Rn. And we're going to compactify Rn in the following way. So there's a 1-1 correspondence between Rn and R algebra homomorphisms from the polynomial ring into R, right? I mean, one direction, if you have a point, you have an evaluation. And the other direction is that if you have an R algebra homomorphism, well, you take the images of the coordinate functions and you get a point. It's that elementary. And now the idea is to replace this R here by larger fields, in fact by ordered fields. So this brings me to talk a little bit about ordered fields. And you know, there's nothing like an example. Again, if you're lost here, then this is a reset, a complete start over. Let's take the field of rational functions. Okay. So I'm going to tell you not only this is ordered field, but there are many orders. So so there is the order plus infinity. So here is the most important point about the rational function. It's outside finitely many points that are the union of the zeros and the points of indeterminacy. The rational function has a well-defined sign. So now you can declare that R is positive if R of t is positive for t large. So this produces one order. For example, in this ordering here, x is larger than any real number r. So there are infinitely large elements. So when you say infinitely large elements, usually people think something metaphysically is behind this. But you know, it's just for every real r, x minus r eventually is positive. That's all it means. But these infinitely large elements are important. Well, there's the analogon for minus infinity. And then every real number A produces two orderings. A plus are positive if on the left of A R is positive and A minus, no, this is on the right of A, I'm sorry. If on the left so R of t comes with all these orderings, and you can, at lunch you can solve this exercise. The idea is the following. You have x, and you have r, and you're supposed to have an ordering. Now you can ask yourself, well, you know, if I have a real number, it's either smaller than x or larger than x, right? So maybe it's smaller than x. Maybe it's smaller than x for all the reals, and then that's the ordering. Or it determines a Dedekind cut, and that leads, after a small discussion, to this. So this is a lovely fact. Now the problem we're facing here is that this is an ordered field, but it lacks a lot of things we like about the real numbers. And what we like about the real numbers is that we understand completely the linear algebra over the real numbers. You know, when are quadratic forms equivalent, and that's what I mean. And here, of course, this field has a big disease. Let's say if you take this ordering here, then even though x is as positive as it gets, square root of x is not in here. So suddenly we have put ourselves in a situation where an infinite number of complications, because our field, there are not enough equations we can solve. So we want ordered fields F whose linear algebra over F is the same than the linear algebra over R. So of course, that's slightly imprecise. So we want fields that are real closed. So a field is real, an ordered field is real closed if every positive element is a square and every odd degree polynomial has a root in F. So these are the fields where anything you can express in the first order language of ordered fields over R, any sentence that's true over R expressed in the first order language or ordered fields is also true here. So any problem in linear algebra you can solve over R, you can solve it over F. That will become important later on. And then the final fact is every ordered field has a unique real closure. It's the analog of the algebraic closure of a field, but here it's just the largest field to which the order of the largest algebraic extension to which the order of K extends. So you will see that for every one of these orders here, the real closure is a different kind of field which you can describe in terms of convergent Puiseux series, etc., blah, blah, blah. It is rather concrete in this example. So now I can tell you what is the compactification of Rn. So these are all the pairs consisting of a R algebra homomorphism into F real closed. And what else? Yeah, and then we want that F is algebraic over this ring. And then there is an equivalence relation that comes just from commutative diagrams. So that's a little bit fast. Now, the topology on it is the basis of open sets. If you have a bunch of polynomials here, then you can ask yourself for every polynomial, well, you cannot ask yourself. I mean, you can, then the image of the polynomial in this ordered field, I mean, it's either positive or negative or 0. So, we're looking at all the points in the real spectrum such that the image is positive. This gives the structure of a compact topological space. And it's a feature of this thing that there are closed points and not closed points. So there is a subset consisting of closed points. And now I can draw for you the only picture that there is. I can draw for you the real spectrum compactification of the real line. And in fact, with all the things I told you, it's essentially also an exercise. So here is the real spectrum compactification of R. You have the real line, you have the point plus infinity, minus infinity, then every real number contributes. That's just the evaluation homomorphism to R. And now I need colors. Above A, there are 2 points, A plus and A minus. And those are the non-closed points. They have the property that any neighborhood of A plus contains A. So the set of closed points now looks like that. So that's a perfectly reasonable compactification of R, because it's mindful of the topology, and then for R2 you can't draw it anymore. You seem puzzled by something.
Yeah, I'm puzzled.
Yeah.
When you were talking about the orderings of R, for each real number there were 2 orderings. Right?
Yeah.
The real number itself doesn't correspond to anything because there are polynomials that evaluate 0.
Yeah.
So I'm not seeing the closed points in the definition.
So the closed
I see
point.
the non-closed points.
The closed points correspond either to the homomorphisms into R,
Yeah.
so this gives all the reals,
Okay.
and the homomorphism into
Into
R
the
of X,
extension.
R of X with this ordering,
Uh-huh.
and R of X with this ordering.
Okay.
And then there are the others. But by the way, now I'm a little bit worried. So 1537 means I still have 15 minutes, or?
Yeah, 15 minutes. Look at 5.
Sorry?
Look at 5 minutes.
5 minutes.
Yeah.
7.
All right. Okay. So now we can compactify real algebraic sets with this. And now I'm going to skip an infinite number of things. So I've compactified Rn, and so I can compactify my character right. And our first theorem gives an interpretation of the point. So we have a compact space. It is a compactification of, in fact, it is a compactification of the character variety. And not only this, but there is an observation of Brumfield that says that the check homology of the compactification coincides with the usual homology of the character variety. So now you have compactified this in such a way that all the connected components are preserved. If you have something that's contractible, then you know the homology of the compactification, etc. So, okay, so points in the real spectrum boundary of the character variety are in 1-1 correspondence with equivalence classes of representations. Remember the GF. Rho is reductive, F is real closed minimal, non-Archimedean. The minimality is something that is really comes from as being real close. It means that this representation cannot be conjugated into the L points of G for L a strictly smaller real closed field. So in a sense, that doesn't happen often, that to pin down the minimal field of definition in an invariant way, by the way. So now, yeah, non-Archimedean, we know what it is. There is some equivalence that involves isomorphism between fields and conjugation. And to finish, I have to say, where does this lead to? First, there's the thesis of my student Appenzeller, who shows that points in the real spectrum boundary lead canonically to gamma actions on lambda billions. So and lambda is a finitely generated, is a finite dimensional Q vector space in R with the ordering. Well, now let's come back to our examples. Well, you know, if you take the real spectrum compactification of Teichmüller space, then you can ask yourself, okay, I know that all the points are represented by representations into PSL2F, blah, blah, blah. Can I characterize them? Answer is yes. In terms of Euler number. Can you characterize the points in the real spectrum compactification of the Hitchin component? Yes. In terms of positivity. So that's the thesis of Xenia Flamm. And I'm going to finish with the following theorem, which tells you the difference between the real between the Thurston compactification and the real spectrum compactification. Is that stabilizers in the mapping class group of points in the real spectrum boundary are virtually abelian. That's of course a very big difference between, because in the first compactification you can just have pinched one separating geodesic. And then you have the product of mapping class groups of smaller surfaces. So this thing here looks more like, the question being then whether this action is topologically amenable and etc. etc. Okay, I don't know. Okay, only 40 seconds over time. Thanks for your attention.
Sorry, maybe I missed something. I'm slightly
Yeah.
confused about how to reconcile this claim that there's a unique real closure with the statements about F being the minimal real closed field with F varying even with F.
Okay, it's not unique. It's if you have a ordered field K, then there is a real closure that is unique up to unique isomorphism over K.
Right.
That is sort of absolutely fundamental if you put equivalence relations. I mean, for algebraic closure, it's so wrong.
Sure, but in your definition of spec, the F is varying, right?
Yeah, I have this equivalence relation here,
Yeah, does that include
which is
what
that
you just said or not?
two pairs phi1, f1, phi2, f2 are equivalent if there is an isomorphism from f1 to f2 that makes the diagram commute. Sorry, yeah, that has to be said.
So in the minimality statement somehow, I guess so. Then I'm confused.
So
Is F still just sitting inside itself?
These are-
Is that why it's minimal?
okay, I'm sorry. So I should have said classes of pairs rho f. Now I have to say what the equivalence is. So, you know, if you have, there are two things you can do, conjugation over f, or change the field to an isomorphic field.
Yeah.
And the diagram commutes. Yeah, well, yeah, if one gives a proper course on that, then one would have to say. And then one would have to convince people that what I'm writing down on the blackboard is a set. Okay? I mean, because all the... because there is a different description in terms of, you can think of such a thing here. Well, I look at the kernel so you can get the prime ideal. And now you can just focus on the prime ideals such that if you look at the corresponding fraction field, the quotient, you have an ordering. And that's, so the difference with the Zariski spectrum here is that if you go by the quotient of the prime ideal take fraction field, that there are many orderings. That gives the richness of the thing. And then there are also prime ideals here, such that the fraction field is not orderable. R polynomial R of x modulo x squared plus 1. You get C. So it picks up certain prime ideals and a lot of information on all the possible ordering and leaves out other prime ideals.
So what kind of object is the compactified character variety? Is it also a semi-algebraic set? Is that
Well, there are some general facts about compactifying semi-algebraic sets that you can write them as inverse limits of true real algebraic compactifications. I mean, a real algebraic set can always be compactified by some stupid function that sends, x over x squared plus 1, whatever.
Yeah.
And then you look at all possible such things in growing dimensions, you make an inverse system out of that, and it can be seen as that.
And the double racked up is finiteness that says that you don't need to look at all of that. Okay, never mind.
Look, I had an email exchange, and maybe you will understand, with Brumfield, who said one should not look at it as a topological space, just one should look at it as a Noetherian topos, whatever that means. So the word Noetherian has. Yeah, it's interesting. You can define, while continuous semi-algebraic functions don't form a sheaf, because you can show that continuous semi-algebraic functions extend to the real spectrum compactification. You can make a sheaf out of it.
Okay.